So here's our new machine. Okay, this idea of a state register and a combinational logic cloud. We have a notion of a current state that comes out, k bits of some, k seems to be our little index we often use to count the number of state bits. The combinational logic, in combination with the input bits, produces a new state and some output bits. So remember, the combinational logic is an acyclic graph that obeys the static discipline, and we can describe it completely with a truth table. Right? And since it has k plus m inputs, the truth table has to account for all possible combinations of those k plus m bits. So the truth table will have 2 to the k plus m rows. So all possible combinations of the k state bits and the m input bits. The engineered cycle is the only place, so this, even though it looks like a cycle, remember there's no pass-through path here. There's no combinational path from the D to the Q. In fact, we carefully built this clever little double gate mechanism to make sure there is no combinational path. There is no cycle in here. The engineered cycles that's referred to is in fact the positive feedback loop inside the latches. We've spent a lot of time, or as an engineer you would have spent a lot of time guaranteeing that little cyclic circuit actually works correctly, and transitioning from pass-through mode to storage mode, lenient muxes and careful timing and the setup and hold time. That's what all that's about. The engineering has gone in to make those cycles reliable for us. Okay, and remember, setup and hold time. Whenever you see a register, the first thing you should think of is setup and hold times, setup and hold times. Then you look at the hand that has that little inscription on it that you did. There are times when Harry Potter sort of had it right. Okay, and so there's k state bits, so that can represent one of 2 to the k possible combinations of those state bits. Each one can be 0 or 1. We do have to respect the timing assumptions. And so typically the timing problems that you see look a lot like this one, right? Where we give you a bunch of numbers, often one of them has a question mark. And using those 2 timing equations, we can figure out the value for the question mark. Yes?
One register just keeps track of 1 bit, right? So if you want k bits, you're going to need a bunch of...
You need k of those individual 1-bit registers. We often draw them as a single box and just somehow indicate that there's k bits coming in and k bits going out. And you should just know that that's k copies of the single D register that we've been talking about. So we can have a sort of a sloppy notation, but it tends not to be ambiguous. You just have to look at the number of bits that are being stored there. And you say, oh, I need as many individual register bits as the bits I'm trying to remember. So in this particular case, let's answer this question. Constraints on TCD for the logic? Well, we do have this problem of we need the sum of the contamination delays, so 1 plus question mark has to be bigger than the hold time, which is 2. So 1 plus question mark has to be greater than or equal to 2, suggests that the question mark has to be at least greater than 1. The minimum clock period, well, the propagation delay of the register plus the propagation delay of the combinational logic plus the setup time all has to fit in 1 clock cycle. So in this case it's 3 plus 5, which is 8, plus the setup time, which is 2, which is 10. And so we need a clock period a minimum clock period of 10 for this circuit to work correctly. If I run it at 9, the circuit will be flaky. And if any of you try overclocking at home, often what happens is when you're making your processor go faster and faster, making the clock faster and faster and faster, at some point you end up violating this particular timing constraint, and now the circuit is no longer performing correctly and your operating system crashes, and you say, well, maybe it's actually not a 5 gigahertz processor, and you turn it back, down your clock a little bit. Okay. So that's sort of the mechanics of the building blocks. Let's think a little bit about how to build something using these building blocks. So we're going to start with a very simple example. We have a more interesting one towards the end of lecture. So what I want to build is a combination lock. So this is a synchronous circuit. It has a clock. And the idea is that I'm going to put a new input. The in is a single bit, 0 or 1. And I'm going to feed this circuit with a sequence of inputs. And what I would like to do is, and then every time I put a new value on the input signal, I'm going to make the clock have a rising edge so that it can consume that new input and then figure out whether I've entered the correct combination. And we would like our clock to open, to assert the unlock signal, that's the output. So we want U to be 1 if the last 4 values of in that I've clocked into the circuit are 0, 1, 1, 0. And just so that we completely connect the dots here, this is a sequence of inputs we'd like our circuit to process. We can't do that with combinational logic, where the output is always a function of the current inputs. Since we want to process a sequence of inputs, we'll need sequential logic, and sequential logic always involves these state elements which get clocked. Everybody sort of happy with that? So that's the basic strategy. We're going to spend a moment now designing the inside of that circuit. So we're going to introduce a new abstraction to help us think about that. Okay, and this is a very handy abstraction. Whenever I go out in the outside world to design circuits for people, you often will find me surrounded by napkins and engineering notebooks full of the diagrams I'm about to show you, because this is how you actually design sequential circuits. Okay, so again, the numerology is I have a certain number of states in my finite state machine. I have a certain number of inputs m and outputs n. And then I'm going to show you these two rules. Okay, so a finite state machine, basically you have states and then something happens and you go to a new state or to the next state. And the next state may be the state you were in, but it could be a different state. And so what we're going to do is build ourselves a little roadmap of how we get from state to state to state. Sort of like, Google Maps, except it's for state machines. It shows us how we're going to transition among the 2 to the k possible states of the state machine. Okay, so we're going to design our lock. And so here's our first state. Now, all the states, well, typically when you design a state machine, they have a meaning associated with each state. There's a little piece that you can say, I know it to be, for my machine to be in this state. In other words, what's the value in the state registers, those k bits of state registers, the encoded value would tell me I'm in a particular state, and I associate some semantics with that state. So in my lock, the first starting state is a state I've not seen any combination at all. Right, so I've given I've used S for state and then X to sort of say I haven't seen any combination. So I'm trying to give my little state a name. For each state I'm going to indicate what the output I want to, in this case the unlock line, what output I would like associated with that state. And in this case, because we haven't seen any combination, we sure don't want to be unlocking the lock. And then finally, we identify one of the states as the starting state. So we have to design the hardware for this to be true, but at this level of abstraction, we want to identify conceptually where's the start of our journey through all the states. Okay, so we indicate that by a heavy line. Now, when we think about the combination, remember there's, in a sense, a 4-long sequence that we want to remember. And that suggests that what we're going to need, okay, is a set of states that represent successive bits of the combination arriving. So we have the state that we get to after knowing nothing is if the user types in a 0, we will say, oh, that's great. That's actually the first digit of the combination. So I want to remember that I've seen the first digit. So this state, S0, is distinguished from the first state in that this represents having seen the first digit of the combination. And in fact, notice that we've marked the transition, the little map we're making now, that goes from the initial state to this first state, second state, into the next state here. And we've basically said you can go from here to here if the input was a 0. So we're sort of marking down the conditions under which you make a transition from the initial state into S0. And similarly, we're going to have the other states that we need that represent the 4 digits. So 0, 1, 1, 0. So if those were the digits I typed in a row, and each time after I put in the new digit, I made a rising edge of the clock, I would hope that I'm designing my machine to go through this sequence of states. And when it gets to this last state, notice that this state represents having seen the 4 bits of the combination, I'm going to say, aha, this is when I do the unlock. But I sort of get, so this is sort of like, okay, I've tried to organize my thinking about the exact sequence of events, and I have a state that represents every step along that sequence. Well, you can ask yourself, you can say, okay, I think I get this. I can see how this machine, that if I typed in exactly those bits and then did a rising clock edge after each new bit, how I would make a journey from the initial state down to a state where the unlock signal would be asserted. But what happens if after typing a 0, I don't type the correct thing. I type another 0. So what we're going to do is we're going to handle all the other transitions in the diagram. So for example, if I just come in and start typing 1s, which is no part of the combination, even though I've seen some bits, I haven't seen the first digit of the combination yet. Okay, so there's this notion of staying in a state when you haven't seen the condition that you need to get to the next state in the sequence. And so forth and so on. Now some of these arrows may confuse you a little bit. So for example, why is it after I've typed in a 0 and a 1, which puts me in this state here, why is it when I see a 0 I just don't go back to the beginning? You can sort of say to yourself, okay, so 0, 1, that's good. 0 is not the correct next digit, so I should, I'm going to go, shouldn't I just go back? Start over? Instead, I've chosen to go back in this state. And the question is why? Yeah?
That state represents you've seen 1, 0, and if you type 0, 1, 0, ignore the first 2 digits and say, oh, well, okay.
Right. So this is clearly a mistake here. So what you're saying is that this is actually giving away all my plot twists. Okay. So I've typed in 0 and 1. What I've done is I've typed in another 0, and that's not correct. So we know we're not there. But if the person goes ahead and types this, they're expecting this to work. Right? So what I have to do is to make sure that every time I see a new digit, I think of myself, I can say, well, that's not correct for the combination I was processing, but it may be the prefix of another combination somebody's trying to enter. So I make the arrows in my diagram sort of reflect that.